All right. Pointer stick here. And so I'm Brian Granger, and here at ITAMP. And my connection to Ugo Fano is that about a year ago I finished up my PhD with Chris Green at the University of Colorado. And I think I'm one of the younger academic grandchildren of Ugo Fano. I won't go into exactly how young I am. And today I'm going to be talking about using scattering matrices to describe a system where perturbation theory doesn't work. And we've heard some other talks in this section about what happens when you apply non-perturbative laser fields. There won't be non-perturbative laser fields in my talk. For my talk, we'll have strong magnetic fields. All the laser fields will be weak in the dipole limit. And so let's move on. So, well, that is not what we wanted. So we can again pay our thanks to Bill Gates and cohorts. And let's try this again. There. I better not touch it. So what can you expect from this talk? First of all, I'm going to be talking about so-called diamagnetic atoms, where the magnetic field is strong enough that not just the Zeeman term is important, but also the term in the Hamiltonian that's the square of the magnetic field strength. And these systems have a very complicated absorption spectrum. So complicated that you need new ways of thinking about spectroscopy. You can no longer do a line-by-line classification of the absorption peaks. And the way of thinking that's proved most useful for these systems is working in the time domain, or the Fourier domain. And this was initiated by John Delos over a decade ago now. And I'm going to give you a quick sort of review of this and then talk about some limitations of this theory. And these limitations are what got Chris and then myself interested in this problem. And these limitations are related to the ability of closed orbit theory to treat atoms other than very light atoms, such as hydrogen, lithium, helium. And what we've developed is a formulation of this problem that involves scattering matrices. And so I'll talk about these scattering matrices, how they determine the photoabsorption cross-section. And then the key point of my talk will be that you can use these scattering matrices to extract new physics. And I'll apply this methodology to talk about some of the non-classical features in the photoabsorption spectrum that don't have classical analogs with closed orbit theory. So why talk about diamagnetic hydrogen? One, it's a very simple system, right? Two particles. It's experimentally accessible. A lot of experiments have been done on hydrogen and also helium and lithium. It's an example of a non-integrable system in two dimensions. Here I show the Hamiltonian. I'm using the approximation where the proton's infinitely heavy. You see the spherically symmetric Coulomb potential. You have the Zeeman term, and then the cylindrically symmetric diamagnetic potential. And it's the competition between the spherical symmetry and the cylindrical symmetry that causes this system to be non-integrable. Now you might think, well, maybe this is amenable to something like a frame transformation. And the difficulty is the long-range tail of the Coulomb potential. You have to go very, very, very far out before you can start to think of the system as being truly cylindrical. And it's this competition that really provides all the complications. This system's also becoming more relevant in the last few years as people are trying to form anti-hydrogen. And Jerry Gabriels will be talking about this tomorrow. What makes that interesting is they're doing these experiments in a penning trap. They have antiprotons and positrons, and this penning trap has a 5 Tesla magnetic field. So this is not going to be just your average anti-hydrogen. For my talk, I'm going to use a little bit odd energy and time units. These are scaled variables. The only thing you need to worry about here is that what I call energy is on an effective quantum number scale. So it makes the Rydberg series evenly spaced. The time scale for these scaled units actually turns out to be the classical action. This scaled energy is a parameter that determines how chaotic or non-integrable the system is. And the way to think about this is that you can get non-integrability two ways. One, you can just get more highly excited Rydberg states. The other way is increasing the magnetic field strength. And it actually turns out to be this combination of the energy and magnetic field that determines how chaotic the system is. And you can see here, as the scaled energy varies, the system goes from being having all regular or non-chaotic orbits to having chaotic orbits as the scaled energy comes up towards zero. Today I'm going to be talking about spectra taken at scaled energy of minus 0.3, so a good fraction of phase space is chaotic. But I emphasize that this scaled energy will be held fixed as the spectra is taken. What's varied is this other energy that I put in quotes, this effective quantum number scale. And this is done because it keeps the classical dynamics constant. So what does the spectrum look like? Here's an example. This is the photoabsorption spectrum as a function of the energy. This translates to fields of 7 Tesla to 0.47 Tesla, principal quantum numbers of 41 up to n equals 100. And what you see here is a very high density of states, and you see very irregular patterns. And what I want to emphasize is that all the usual quantum numbers that we would go in traditional spectroscopy and label these absorption peaks with are no longer good quantum numbers. The spherical symmetry has been strongly broken by the diamagnetic term in the Hamiltonian. And so you need new ways of thinking about this. And someone thought at some point, well, let's take the Fourier transform. And what you see in this time domain is a sequence of sharp peaks. And now you can think, well, maybe let's not worry about labeling specific peaks in the energy domain, but let's go and interpret peaks in the time domain. And it was sort of, I think, chance that this happened. The initial experiments that were done, they did not have very high resolution lasers. So the initial experiments that they took, or the spectra that they took in this system, showed very broad oscillations of the cross-section with energy. And what they were probing was the very short time peaks in this time domain. And so the way to think about it is that these short time peaks give the broad energy oscillations in the spectrum. And the first theory of this, to really give insight as to what these peaks were, was closed orbit theory. And this was done by Du and Delos in '88. And the basic idea was to represent the photoabsorption cross-section by a smooth piece that's constant with energy, and then a sum of oscillating terms, where each of these oscillating terms has an amplitude that's given by the classical stability of these orbits, and then the period of these oscillations is given by the period of these orbits. And these are called closed orbits because these are classical orbits of the system that begin at the proton, go out into the magnetic field, and then return. So this orbit here is called the quasi-Landau orbit. So it starts here, comes out, gets reflected by the magnetic field, and comes back. And there's balloon orbits, orbits that go out parallel to the magnetic field, and there's also other names like Pac-Man and so on. So by calculating the properties of these orbits, you get a very nice interpretive picture of the photoabsorption spectrum, or this recurrent spectrum, the Fourier transform. And you're wondering, well, how well does this work? And I'm showing you here Fourier transform spectrum for hydrogen and lithium. The top of each of these is a quantum calculation that we've done using B-splines and R matrices. And below is the result of closed orbit theory, basically. And you see basically excellent agreement. One thing I do want to note is for the case of lithium, you see additional peaks that are not seen in the case of hydrogen. And what these are cases where the electron goes out in one closed orbit, and then the non-hydrogenic core of lithium, right, there's a quantum defect, scatters the electron into a different closed orbit. And so you see time domain peaks at the sum of the periods of those two primitive orbits.
Brian?
Yes?
How far out can you go in time and still see this kind of
Actually, they've done experiments far beyond the time I've shown here. And actually, the theory agrees very, very well out there as well. The way we're doing it here, it's more difficult to go out to long times, but that's been looked at. So, but there are limitations of closed orbit theory. First, closed orbit theory fails when you have an ionic core that has non-hydrogenic behavior in higher partial waves. So for instance, rubidium has a large D-wave quantum defect, and closed orbit theory does not do well. And the difficulty is closed orbit theory has radially outgoing trajectories, classical trajectories that are launched with zero angular momentum at the ionic core. The difficulty with that is that at some point the correspondence principle is going to come in. To represent a D-wave wave function, you need classical trajectories that are launched with finite angular momentum. And so that causes closed orbit theory to fail. Another difficulty is that not all quantum mechanical paths are classical or have classical analogs. These are called ghost orbits, when you see quantum paths that do not have classical analogs, at least in this language. Another difficulty is that the Coulomb singularity, nearby this, the semiclassical approximation breakdowns. You get diffractive effects. However, closed orbit theory has a lot of things that I think Ugo Fano would have really liked. It gives a very nice interpretation of the spectrum, and when it does work, it's very numerically efficient. What's that? No. Quantum defect theory, something closer to what has been talked about here. This is nice because the short-range parameters that define the ionic core are independent of energy in a lot of cases. The long-range parameters depend strongly on the energy, but have very simple analytical forms usually. This is nice because you can get a very accurate treatment of the ionic core in non-classical effects, and also, in most cases, it's numerically efficient. And there's one problem, though, that you're faced with, and that the usual formulation of quantum defect theory, even if you use a frame transformation, assumes that the long-range physics is simple in some coordinate system. And the difficulty here is that that's not the case. And so what we've done is sort of combine ideas from both of these theoretical methods and use scattering matrices. And I want to describe how we do that. First of all, there's a familiar short-range scattering matrix that's related to the quantum defects for single electron, single channel systems. I think that's very familiar to everyone. In addition to the short-range scattering matrix, we defined a long-range scattering matrix. And the way to think about this is there's a distance, a radial distance, where the magnetic field is not important. That is, the Coulomb field dominates, but you're still outside the ionic core. And in this region, the physics is purely Coulombic. And what you do is define a scattering matrix to scatter outward from this surface in the Coulomb region and then come back in a different partial wave. And we've been able to show that, similar to closed orbit theory, that this long-range scattering matrix is related to these closed orbits. And here now, this is a matrix here that's related to classical stability of these orbits again, and it's basically constant with energy. Now, all the energy dependence goes into this phase, e to the it, where t is the period of these closed orbits. And you start to see a form of the long-range physics that has a very simple parametrization of the energy dependence. And that's really nice because you can scan through energies very quickly. It took us a while to figure out what the connection was, but you can show that these scattering matrices are related in a very nice way to the photoabsorption cross-section. And we got to this using a lot of the ideas of Francis Robichaud's pre-convolved quantum defect theory. And this is, in principle, an exact quantum mechanical result in the dipole approximation. This can treat any configuration of external fields. So you could have crossed electric and magnetic fields, just electric fields. If you can find the short-range scattering matrix and dipole vectors for an atom without the external fields, then this expression can treat that atom in external fields. And I should mention that this gives the energy smooth cross-section. So you evaluate this cross-section at a small complex energy, and that gives the convolved cross-section convolved with the Lorentzian of the complex part of the energy. And this is nice because below threshold, where normally you would have delta function absorption peaks theoretically, it gives you a smooth function of the energy that's closer to what you would actually measure experimentally. So I want to talk about how you can now use this cross-section with these scattering matrices to interpret, to get some physics out. And what you do is you actually can see that in this previous slide, that this here can be expanded in a geometric series. And once you've done that, you see that the cross-section is a sum over amplitudes, right? There's an amplitude where no scattering, the electron doesn't scatter off the long-range field or the core region, and this gives a smooth piece to the cross-section. There's a piece where the electron scatters once off the core and once off the long-range region, and twice. And this is nice to use scattering matrices because we know that scattering matrices are simply quantum mechanical amplitudes, right? In most cases, it's more convenient to use a K-matrix. It's real. It's computationally a little bit nicer than using complex numbers. Here, we're after the interpretation. And because these scattering matrices are related to the quantum amplitudes, it enables us to get at the physics in a nice way. And the key point is that I showed you a semiclassical approximation for this scattering matrix previously. But even when an exact or a highly accurate quantum scattering matrix is used, you still have this type of parametrization. Now, this is now a sum over quantum paths. Some of these quantum paths have classical analogs. Some of them don't. You have a matrix here that's roughly constant with energy. And then you have a nice term that varies as e to the it that gives the analytic energy dependence. And what I want to show you now is that by taking the Fourier transform of individual terms in this cross-section, that we can extract physics and actually get physically insight about the non-classical paths that are in the quantum mechanical scattering matrix. And I'll just mention that to get the full quantum long-range scattering matrix, we do basically a big R matrix calculation using B-splines. So what I'm showing here is a Fourier transform spectrum of hydrogen, but just the first order cross-section. So the piece that corresponds to electron scattering once off the long-range region and once off the core region. Now, again, for hydrogen, quantum defects vanish, so S core is just 1. So this is really probing the physics of the long-range scattering matrix. And what you see is a bunch of absorption peaks. These are scans at different scaled energies. So as you go up this way, the system is becoming more chaotic. And here you can see a bunch of peaks that I've labeled by the corresponding classical orbits. This is the quasi-Landau peak. This is the orbit that was shaped like a bubble. And what you see, that I've labeled by the dotted lines here, are recurrence peaks that have no classical analog. And these are ghost orbits. And here's an example of what a ghost orbit looks like. And I want to show you on the next slide how to think about these orbits. And how you think about them is that they're almost closed orbits, right? So there's a classical orbit here that goes out, and instead of coming back and overlapping with the initial state, it has a nearby collision. So if you zoom up on this, the electron's coming by. Now this is a classical picture, right? Quantum mechanically, that this is a wave. And there's a wave front here, and that wave can tunnel in to the ionic core and actually give a recurrent strength there. And so that's what these ghost orbits are. And we can now actually do a quantum mechanical calculation of their contributions.
Is this a ghost or just an artist's conception? This is an actual classical orbit.
Yeah, this is right. Now,
what happens after it leaves? I mean,
it can. Yeah, actually, it continues to go on and ramble around for a very long time.
All over the place, but occasionally it comes back.
Yes. Now, I should mention, you might think, well, what if I changed the initial angle a little bit? Couldn't I get it to hit? And that's exactly what makes a ghost orbit, is that there's no initial condition that you can pick that would actually get it to hit, right? And so that's a unique feature. So that's what happens when some of the information you can get from this. Yeah.
Can you define the Lyapunov exponent for this orbit?
Absolutely, yeah.
It's always positive?
Yeah, these are unstable periodic orbits. So now I'm going to show you the second order cross section that corresponds to 2 trips of the electron in this long-range region. And what you see is peaks at twice the period of the primitive orbits, but you also see peaks here that correspond to the combination of 2 primitive orbits. And so this dotted line here corresponds to the combination of the quasi-Landau and the bubble orbit, and you can also see some other peaks. And these are what I'm calling combination orbits. When you have a non-hydrogenic atom, people are calling these core scattered orbits. And for those of you familiar with closed orbit theory, this should actually trouble you that we're seeing this for hydrogen. And that the reason that this is troubling is the following. And that the classical Coulomb scattering at low angular momentum is strongly backscattered. So if I go out in a classical orbit, come back here, when I approach the Coulomb singularity, the magnetic field's not important, so I'm going to get sent back out and just repeat that orbit in the opposite direction. Right? It's impossible, classically, for the electron to go out in a given orbit and then scatter into a different orbit. And this was used initially in closed orbit theory to argue that these combination orbits would not be there for hydrogen. But then you start to think, and that the difficulty is that the semiclassical approximation is breaking down near the Coulomb singularity, right? When you get back close to the Coulomb singularity, the potential is varying strongly compared to the wavelength of the electron, and you get these diffractive effects. And so actually, we shouldn't be surprised that these orbits are there. Now, they're small, but they are there. And sort of the punchline of this part is that these ghost orbits that I talked about and these combination orbits that occur at different orders in this cross-section have a lot of similarities. First of all, they appear at similar actions. If I were to overlay the first order and second order cross-sections, you'd see that they always appear at the same actions. You'd also see that the height of their recurrence peak is the same. And here's some example of how they have similar topologies. So here's a combination orbit, and then here is a ghost orbit. Now here I've actually shown the ghost orbit after it bifurcates into a real existing classical orbit. Here's another example, and you can see they have similar shapes. And in all the work we've done, this relationship between the ghost orbits and the combined orbit seems to be universal, right? And to some extent, that's not surprising, right? When an electron goes out as an actual quantum mechanical wave, it's not just this path, but all the nearby paths contribute as well. And you can see that the shapes are roughly the same, and so all these two different orbits are part of that same quantum mechanical wave. So there's one other trick, though, and it's when you combine this first order and the second order cross-section, you find no trace of either the ghost orbits or the core scattered orbits. They would appear here, here, here. And so what you realize is that there's something subtle going on here. This classical picture that was initially used with closed orbit theory to argue that you wouldn't see these effects turns out to be true when you look at the total cross-section. And that there's something sort of mysterious going on with the Coulomb potential, that these paths, these quantum mechanical paths that get flux from one orbit into the other are not there for hydrogen. So you might think, well, if they're not there, I mean, it's really not a real effect. However, there's an important thing, and that's when you have a non-hydrogenic atom, one of these orbits, the combined orbits, picks up a phase due to the quantum defect every time it collides with the core. The ghost orbit, though, never comes close enough to pick up this phase due to the quantum defect. And so you actually get, for non-hydrogenic atoms, an interference between these two paths. And that, including both paths in that case, is very important. It's actually very critical. And so what we've done is look at what are the implications of this cancellation effect for semiclassical theories. So what you can do, again, expand the cross-section in a power series, use a semiclassical scattering matrix, and then by hand go in and rearrange all the different terms and cancel the combined orbits with the ghost orbits. And I emphasize that at this point, there's not a semiclassical theory, at least a complete semiclassical theory, for these two contributions in hydrogen. At this point, this is an ad hoc cancellation that we're postulating based on these accurate quantum calculations we're doing. So you do this cancellation, and you find the following form for the semiclassical cross-section. You see this linear term, then you see that the quadratic term the core scattering now is not mediated by the core region scattering matrix, but 1 minus the core region scattering matrix. What's nice about this is that for hydrogen, this is unity. This term vanishes, and you only see the linear term. And so this turns out to be exactly the result of closed orbit theory. And so what this tells us is that somehow closed orbit theory is much more subtle and intelligent, actually, than you might initially think. You might think, well, that it's not including any non-classical paths. And that's, I think, traditionally been the view of closed orbit theory. But by a bit of luck, it turns out that it is including, through this cancellation, these effects. One thing that, just notationally, that our notation has enabled us to do is you can realize that, again, this is just a geometric series. You can actually resum this series. And what's nice about this is that you can now represent semiclassically all orders of core scattering analytically. And that's a new result. Typically in closed orbit theory, these type expansions have to be carried out term by term. And one subtle piece is that it looks like for atoms like rubidium that have strong D-wave quantum defects, this series actually diverges. And it's been sort of an ongoing mystery as to why this series diverges. When does it diverge? And one thing that being able to resum this series enables you to do is it's a geometric series. You know its convergence properties. And so it allows you to study that in a very controlled manner. So just to conclude, I've shown you how the scattering matrices provide a complete and convenient framework for studying atomic photoabsorption in external fields. I've shown you work on the magnetic field. I also want to mention that we've recently started to look at the electric field case. And we've started to combine Harman's ideas of frame transformations using the parabolic coordinates for the long-range physics. And we have now an analytical form of this long-range scattering matrix for the electric field effect. And so we're hoping to use all these same ideas to look at Stark physics as well. These partial cross-sections yield new physics about non-classical paths. Now, these are not partial cross-sections as we usually think of them. These are the individual terms in this power series of the expansion. These ghost orbit and combined orbits cancel in hydrogen, and this leads to the familiar result of closed orbit theory and sort of gives you new insight about that. And then most importantly, closed orbit theory, or our theory with the scattering matrices, can actually be resummed into a closed form expression